Welcome back. Today I would like to talk to you about Taylor and Maclaurin series. And so I guess the big question that we want to answer today is, how do you actually find a power series expansion for a function? Okay, so what we want to start out with today is let's just look at a function f of x, and let's say that this function actually does have a power series expansion. Okay, if it does, this is what it looks like. It looks like the sum in going from 0 to infinity of a sub n times x minus a to the n. All right, so this is what it would look like if this function did have a power series. Okay, that's what all power series look like. Now, I'm going to write this out a little bit longer. And so if a were equal to 0, then this would be a sub 0 times x minus a to the 0 power. But x minus a to the 0 power is just 1, so it's just a0. Plus, if n is 1, I get a1 times x minus a to the first. Plus, if n is 2, I get a2 times x minus a squared. Plus, let's write another one, a3 times x minus a cubed, plus, and so on. Okay, so that is the long way of writing out this power series expansion. Now, what is A here? A is what we call the center of the power series. Okay, so when you're calculating radius of convergence, it has a center, and that center is A. Okay, so A is a known number, and we get to pick the center of our Taylor series typically. So A is just a constant. So really, to know what the power series expansion is for a particular f of x, what I really want to know is what's a0, what's a1, what's a2, what's a3, and so on. If I knew all those coefficients, I'd be done. That's the whole thing. I just need to know these a sub k coefficients. So what I'm going to do is I'm going to develop a way for you to find those coefficients. All right, so if this is my original function, f of x, then let's take the derivative of that function, f prime of x. Okay, so the derivative of a sub 0 is 0. So I'll just write for now 0 plus the derivative of a1 times x and then a1 times a. a1 times x's derivative is a1, and a1 times negative a's derivative is 0. So it's just a1. What's the derivative of the next term, the a2 times x minus a squared? Well, that's a chain rule problem, and so I'd get plus 2a2 x minus a to the first. Then the next one, use the chain rule again, and I get 3a3 times x minus a squared. Plus, maybe you could see what the next one would be. It would be 4a4 times x minus a cubed, and so on. All right, let's take another derivative. So I get f double prime of x. The 0 is kind of gone. The derivative of a1 would be 0. The derivative of 2a2 x minus a would just be 2a2. And the next one, the derivative by the chain rule would be 6a3 times x minus a. The derivative of the next guy would be plus 12a4 times x minus a squared, plus, and so on. Let's do another one. Third derivative. Oops. And so the derivative of 2a2 is 0. The derivative of 6a3 times x minus a is just 6a3. The derivative of the next one would be 24a4 times x minus a plus some other stuff. Let's take the fourth derivative. The derivative of the first one, 0. The derivative of the second one is 24a4 plus some other stuff. Okay, we're getting the idea here. So I have taken all these derivatives, and now the question is, why did I do all of this? Why did I take all these derivatives? Remember, what we're trying to figure out is what are the coefficients. What are the A1, the A0, the A2, the A3, the A4, and so on. So given all of this stuff, what I want to do now is go through and plug in A to each of these equations. So I want to know what is f of A, what's f prime of A, what's f double prime of A. So I'm going to move to the next slide, but feel free to come back to this board state and look at what I'm talking about, because I'm going to erase it right now. So what am I talking about when I say f of A? Well, if I plug in A to that big line of this big power series for every x value, everything goes away except A sub 0. So in other words, f of A is A sub 0. What about f prime of A? Now I plug in A to all of the terms in the f prime equation, and everything will go away except A1. If I plug it into f double prime, if I plug A into f double prime, everything will go away except what? 2A2. If I plug it into f triple prime, everything goes away except the 6A3. And finally, if I plug it into the fourth prime, everything goes away except 24A4, and so on. Okay, I'm going to rewrite this one more time because I want you to see a pattern. This is 0 factorial times A0. This is 1 factorial times A1. This is 2 factorial times A2. This is 3 factorial times A3. This is 4 factorial times A4, and so on. So we are starting to see something here, and now what I could do is I could solve each of these equations for the A0, the A1, the A2. Notice on this side I have 0, A0, and on this side I have f of A. So if I just divide both sides by 0 factorial, which is actually just 1, I get that A0 is equal to f of A divided by 0 factorial. And I get that A1 is equal to f prime of A divided by 1 factorial. And I get that A2 is f double prime of A divided by 2 factorial. And we're starting to see a pattern here. A3 is f triple prime of A divided by 3 factorial, and so on. So here I've just solved for every one of the coefficients I need to put into my power series, as long as I can actually take these derivatives. If I can take those derivatives all the way, then I can find the coefficients I need for this power series. All right, so let's rewrite the power series using this new information. So what I had before is I had that f of x is equal to the sum in going from 0 to infinity of a sub n times x minus a raised to the n power. Now, though, I've solved for all of the a sub n's. So what I get is that now f of x is equal to the sum in going from 0 to infinity, and a sub n ended up being the nth derivative evaluated at a divided by n factorial, and we're still multiplied by x minus a to the n. All right, and this is how we compute a power series if we can take all the derivatives we want to of the function. When we compute a power series in this way, we call this a Taylor series. So this is how we compute a Taylor series, and if a is equal to 0, then we call it a Maclaurin series. So a Taylor series and a Maclaurin series are basically the same thing. They're just a power series. The only difference is that a Maclaurin series is just a Taylor series where a is 0. Okay, so there's nothing super special about a Maclaurin series. It's just a Taylor series where the a value is 0. All right, now I want to show you something that's kind of cool. Let's take a little bit of a look at one specific Taylor series expansion and see what it can teach us about Taylor series. So let me clear this off. And I want to look at the function f of x is equal to sine of x. All right. So when you compute Taylor series, the first thing that you want to do is just take a bunch of derivatives of your function. Okay. So I'm going to take a bunch of derivatives of sine of x. So let's remind ourselves what's f prime of x. The derivative of sine of x is cosine of x. Let's take a second derivative. The derivative of cosine of x is negative sine of x. Let's take a triple derivative. The derivative of negative sine of x is negative cosine of x. We can take a fourth derivative. The derivative of negative cosine of x is sine of x, and we see we're back into a repeating cycle. So if we took a fifth derivative, we would get what? Back to cosine of x, and maybe we get the idea here. Okay, then what we do is we go ahead and plug in our a value. And so I'm going to tell you now what a is. I'm going to assume this is a Maclaurin series, and we're going to let a, the center of this power series, be equal to 0. Okay, then let's plug in a to each of these things. So we get f of 0, and if I plug in 0 to sine of 0 is in fact 0, and then I get f prime of 0, and so that's cosine of 0, which we know is 1. Then I get f double prime of 0, that's negative sine of 0, which is still 0. Then I get f triple prime of 0, which is negative cosine of 0, or negative 1. Then I get the fourth derivative at 0, which is 0. I get the fifth derivative at 0, which is 1. And we start to see the pattern here. Okay, now that we know all of these, we can start to construct the actual Taylor series for sine. Let me write it here at the bottom. So I get that sine of x is equal to, well, the very first term is going to be a0 over 0 factorial times x minus a to the 0. So what is that first term? What's a0? a0 is 0. So what we want to plug in here is it's 0 over 0 factorial times x minus a. What's a? A is 0. So x minus 0 to the 0th power plus the next guy, 1 over 1 factorial times x minus 0. I could keep on writing minus 0, but we get the idea. It's just x to the first plus 0 over 2 factorial times x squared minus 1 over 3 factorial times x cubed plus 0 over 4 factorial times x to the 4th. What would be the next one? Plus 1 over 5 factorial times x to the 5th, plus, and so on. Okay, there's a lot of zeros here, so let's clean this up just a little bit. I could write, this is all just 0, this is 0, this is 0. So this is looking like 1 over 1 factorial, otherwise known as 1. So this is just x. Okay, then I get minus x cubed over 3 factorial. Then I get plus x to the 5th over 5 factorial. We could kind of guess what the next guy is. It's minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial, and so on. And so if I wanted to write this in a closed form and kind of write it more neatly, I might write that this is the sum in going from, we could go from 1 or 0, let's say, to infinity, of, I see it alternates. So since it alternates, I'll write it's negative 1. And do I want the first one to be positive or negative? The x is positive, so I want, when n is 0, I want this thing to be positive, so I'll write to the nth power. So when I plug in 0, I get 1. And then I get x to the, this is always odd, so maybe I call it 2n plus 1 power. That will always make it odd. And then on the bottom, I have that power, 2n plus 1 factorial. So this would be the closed form of that power series expansion. Okay, so that's a great example of how we would compute a Maclaurin series for sine of x. Now that we know about that, let me kind of show you what this is actually doing. Okay, so let's rewrite this for a second. I'll clear that out. And we have that sine of x is equal to, I'll rewrite this, it's x, but I'm going to be kind of clever here, and I'm going to write this in some different colors. I'm going to call it x. Then let's get a different color, and we'll say minus x cubed over 3 factorial. Let's get a different color, plus x to the 5th over 5 factorial, and then let's grab a different color, minus x to the 7th over 7 factorial. And now we'll just make it white again. Plus dot dot dot. Okay. And the reason I do this is I want to draw a graph. We know what sine looks like, right? We know sine does this sort of thing. If this is 1 and minus 1, sine kind of does this sort of deal. And so I want to know, what do these different curves look like? So if I just look at sine of x is just equal to x, so I only look at this piece of the curve, but I don't look at any of the other things, then what would it look like? Well, y equals x just looks like this. So you can see when I'm really close to 0, that actually is pretty close to the actual curve sine of x. But as you get further and further from 0, which by the way is the center of this power series, 0 is the center. That should be key here. It's close to 0. When it's close to 0, we're right on already. When it's far from 0, we're way off. So now what if we added the next term? So let me turn this into blue here, and I will draw the next curve. So if I added on the next curve, it might look something like this. All right. So this is a cubic curve, and I added in this piece. And now you can see it's kind of conforming itself to this sine curve. It's not perfect, but it's closer, a little bit further from the actual sine curve. Now let's move to green. If we were to graph this guy, then it's going to go here to out this way. And let's see, one, and this way. So that looks much more like the sine curve. If we added the yellow curve in, then now it's going to go 1. And it would go all the way out this way. Okay. And you get the idea. So as we add more and more terms of my Taylor series in to this expansion, I'm morphing into the sine curve. And if I wanted to know how accurate is this thing, well, what is the radius of convergence of this power series? And if you did the radius of convergence for this power series for sine of x, you'd see that the radius of convergence was infinite. In other words, this actually works for any value of x if you take the entire power series expansion. Okay? So this is really cool. This is why Taylor series are so amazing, is that we're kind of able to take polynomials. Notice that this is just a polynomial, and get something that's very close to a transcendental function, like sine of x. So sine of x is a very complicated curve with lots of roots, infinitely many, but we can approximate it close to 0 by just taking a few terms of some polynomial. So this is the idea, is how do we morph transcendental functions that are kind of hard to work with into, let's say, a polynomial that's very easy to work with. And we do that through Taylor series. So that's the whole idea behind Taylor series. Let's look at a few other homework examples to really show you how these things work in a homework setting.